Josh Lovell, Product Line Manager for Teledyne Labs Pharmaceutical R&D Products. Thanks for joining our regular chromatography webinar series. Today's topic is focused on how understanding UV can lead to sharper peaks in flash chromatography. As a reminder, if you have any audio-video issues, please exit the webinar and rejoin. This usually resolves the issue. If you have any questions during the webinar, please utilize the Q&A feature. All questions will be answered at the end of the webinar. The webinar will be recorded and made available for future viewings. Today, we are excited to introduce one of Teledyne Labs' in-house application specialists, Dylan Cavey. Dylan is one of several application experts that we have at Teledyne Labs to help customers determine the best route to a successful separation. For any of your tough separation questions, please reach out to any of our experts with your questions. At this point, it's my pleasure to hand it over to Dylan.
Hi everyone, welcome into our first webinar of 2024. As previously mentioned, I'm Dylan Cavey. I'm an applications chemist here at Teledyne Labs, and today we're going to talk everything UV detection, what is UV, and how understanding UV can lead you guys to sharper peaks in flash chromatography. So we're going to give some tips and tricks to lead you guys into pure fractions and higher recovery numbers. So some of you might be aware, others might not be aware, but we are now at Teledyne Labs, and this is the rebranding we're doing for 2024. So we're combining CTAC, Tecmar, ISCO, Hansen, and Lehman Labs into one roof, all under one roof, and that is going to be Teledyne Labs. So now all of your laboratory solutions shown at the bottom half of this slide here are going to be found under Teledyne Labs. And one important thing to note, if you're looking for chromatography, Teledyne ISCO is still going to exist, and that's going to be for our fresh water, our water side of ISCO. So that URL, that website, all of those social medias, those are still going to exist for ISCO, but you're not going to be able to find chromatography under ISCO anymore. That's all going to be under Teledyne Labs. So jot down a quick note about that. Chromatography will be with Teledyne Labs along with all of these other laboratory solutions. So we're going to start off today talking about UV and what is UV. So we're going to give a good definition of what UV is, and then we'll talk about how UV detection actually works. So what's going on within your chromatography instrument that allows you to cut fractions based off of that UV. Then we'll talk about which wavelengths you guys should use for certain compounds. So we'll give some tips to look at which wavelengths you guys should use based on which compounds you guys are using. We'll talk a little bit about UV versus UV-Vis. What's the difference between these two different detectors and when one might be favorable over the other. We'll then touch base on all wavelength detection, when that might be beneficial, and then we'll talk about our baseline correction. So as mentioned, we're going to dive into what is UV. So UV is ultraviolet light. So these are going to be shorter wavelengths than visible light, and they're going to be invisible to the human eye. So if you look at our diagram on the right and you see where that purple box popped up, you can tell that ultraviolet light, UV, is going to have an increased energy compared to what visible light is, and we're going to have a decreased wavelength. Now, if we continue to increase that energy from UV, we're going to get into those X-rays and those gamma rays, and those are going to have smaller wavelengths compared to UV. But if we do the opposite, if we then decrease the energy and increase that wavelength, that's where we're going to transition into the visible light, which is around 400 nanometers to about 800 nanometers. And then if we continue to increase the wavelength from there, we'll get into infrared and radio waves. Now, a lot of the time, our compounds of interest, they're not going to absorb within visible light unless you're working with dyes, or if you're working with some natural products. A lot of the time, our solutions are going to be clear, a lot like the one that is pictured here. It's not going to have any really color to it, so you're not going to find any sort of absorbance with your UV detector in that visible light spectrum from that 400 to that 800 nanometers. A lot of the time they're going to have some sort of UV absorbance of somewhere around 200 to 400 nanometers. So if we look at the spectrum for this compound, you can see that we get a pretty good peak around that 245, 250 nanometers, and you can see also we have some sort of absorbance below 210 nanometers as well. So with UV, there's going to be a couple different ways that we can detect this UV. So a couple different UV detectors, and the first of which being is going to be our fixed wavelength detector. So if we look at this diagram on the right, we have our light source, and that light source is going to travel through our entrance slit, and then it's going to hit this grating. And this grating in a fixed wavelength detector, it's not going to be able to move. It's not going to be able to change its angle. So it's always going to send the same wavelength through the exit slit, through the flow cell, ultimately to the detector. So in this diagram here, it's going to send that green wavelength through the exit slit to the detector every single time. You're not able to change that. Now, the second detector we have on our list, the variable wavelength detector, is going to be able to change the angle of its grating. So it's going to be able to select which wavelength it wants to send through the exit slit, through the flow cell, to the detector by changing the angle of that grating. So you're able then to look at all these different types of wavelengths because of this angle change at the grating, but you're still only able to look at one wavelength at a time. The last detector on our list, this photodiode array, is going to allow you to look at multiple different wavelengths simultaneously. So this one's a little bit different from the variable wavelength detector and the fixed wavelength detector, because now we're going to have the light source, we're going to have the entrance slit, and we're going to then send it through the flow cell, and then it's going to hit the grating, and the grating's going to still split up that light source into its multiple different wavelengths. But then we have these photodiodes that are able to collect information simultaneously with each other. So you're able to look at a 200 nanometer absorbance and a 400 nanometer absorbance all at the same time thanks to these photodiodes. Now, on the previous slides, we talked about UV detectors and the different types of UV detectors. And if you remember from those diagrams, you always saw light source. Well, there's multiple different light sources when we're looking at UV detectors as well. So those could be a deuterium lamp, that could be a tungsten lamp, or a halogen lamp, or even a xenon lamp, are all possible light sources for UV detectors. And with these different light sources, you're going to get different light intensities for these different lamps. So if we look at this chart on the right, you can see that the deuterium lamp has really good light intensity ranging from 200 nanometers up to 400 nanometers. So it'd be a really good choice for UV detection. Now, if we look at this tungsten lamp, it's going to have better light intensity going from 400 nanometers up past 1,000 nanometers. So if you're looking at the visible spectrum, maybe the tungsten lamp is a better choice. Now, the xenon lamp, that's going to have good light intensity going from 100 nanometers up until 1100 nanometers. Know some of the different UV detectors and some of the different light sources. How exactly does UV detection work? What are we sending to those UV detectors? And in order to answer that question, we have to go over some terminologies. To start off, we're going to talk about absorption, which is the transfer of energy. And a lot of the time, if you look at your chromatograms, you're going to see on that y-axis, you're going to have absorbance. So really, the absorbance is just this transfer of energy within your compound. So if we look at this example on the right here, you can see we're sending multiple different wavelengths into this compound, and you can see how that compound absorbs these wavelengths within itself and disperses that energy. Now, the other term we have to be familiar with when we're talking about UV detection is transmission, and this is where these wavelengths are going to go directly through our compound. So the light travels through our compound, and this is actually what's being detected at the UV detectors, is the transmission. Because if you think about it, absorption, there's no way that that light, those wavelengths are going to be sent to the detector because they're being absorbed within your compound. But with transmission, these wavelengths are able to continually go through our compound, through the flow cell, to the detector. So it's actually what's being measured is the transmission at the UV detectors. The last thing we have to talk about in terms of UV detection is reflection, and this is when lights are going to bounce off of a compound. So if we have a purple compound as depicted here, it's going to absorb these different wavelengths. It's going to absorb a red wavelength, an orange, a blue, a green, yellow, so on. And it's going to reflect this purple wavelength. So this is how objects or compounds are able to get their color, is they reflect those wavelengths. So as previously mentioned, detectors are actually going to measure the transmission. So in order to get from transmission to absorbance, we have to use this equation stated here. So we're going to look at the absorbance is equal to the negative log of the transmission through the sample over the transmission with no sample. So in order to better illustrate this, we're going to look at an example with this blue compound shown here. So we have 3 arrows of each color or each wavelength being sent through this compound, and you can see how many of these wavelengths or these arrows are transmitted on the right hand side. So if we look at those red arrows, we're transmitting 100% of those red arrows. 3 start on the left-hand side and 3 come out on the other side of the compound. 66% of the green arrows are going to be transmitted, and then only 33% of our blue arrows are going to be transmitted. Now, when we plug these into our equation shown here to measure the absorption of our different wavelengths, you can see that we get 0 absorbance for our red wavelength, and that's because, again, we start with 3 on the left hand side, and then 3 of those red arrows are going to be transmitted through our compound. Since we get 1 of those green arrows absorbed within our compound, we're going to see some sort of absorbance because absorbance is taking place. So we're going to get a 0.18 absorbance for this green wavelength because only 2 of those arrows are being transmitted. And then, of course, with these blue arrows, our absorbance is going to go up again because we're absorbing 2 of those arrows this time, and only 1 arrow is being transmitted. So we're going to get an absorbance of 0.48. So the absorbance is going to equal the negative log of our transmit. So if we look again at those red arrows, 100% of those were transmitted. So our absorbance is going to be 0 because everything was transmitted. There was no absorbance being taken place. Now, if you have an absorbance of 1, that's going to equal to about 10% of your light being transmitted, again, because this is a log scale. Now, the other thing we could look at here is a couple different dyes to better illustrate this. So if you have a blue dye, it's going to transmit these red, these orange, these yellow wavelengths, and it's going to absorb those blue and green wavelengths. So it's a little bit different than what you would expect to see if you're looking at a blue dye. You might expect a peak within that blue region, but that's what it's absorbing, and it's not transmitting. Same with the red dye, it's going to absorb those red wavelengths, so you're not going to see any sort of transmission within those wavelengths. The transmission is going to come in those blue, those green wavelengths. When we're talking about UV, we also have to bring up a chromophore. And so what is a chromophore? Well, a chromophore is really just a group of atoms that are responsible for either the color or the absorption of a compound. So these group of atoms are what are actually absorbing those certain wavelengths of light. So if you guys remember back earlier, we talked about absorbance, how that energy is dispersed within that compound. Well, that's what these chromophores are doing. So these chromophores are typically double bonds, aromatic rings, or non-bonding orbitals found within your compounds. And when they absorb these certain wavelengths, they go from a ground state to one of these excited states. So here depicted is 3 different transitions that are most popular within the UV range. So from 200 nanometers up to 400 nanometers, these are the type of transitions that we're going to see with these chromophores, is one of these 3 transitions. So we can look at an example here. Let's look at ethyl acetate, which the structure of ethyl acetate is in the bottom left hand corner of your screen here, and you can see it has a double bond. And it also has some non-bonding orbitals, and the spectrum, that red trace is shown there. That's its UV spectrum. So anything below 240 nanometers for ethyl acetate, we're going to have some sort of UV absorbance. So that means that these chromophores found within ethyl acetate are absorbing some of these shorter wavelengths, high energy wavelengths found below 240 nanometers, and it's going through one of these three transitions to give off some UV signal. Same could be said for DMSO. Now DMSO has the same one double bond, has some non-bonding orbitals along with it, but it's only going to have some UV signal below 220 nanometers. So it needs a little bit higher energy wavelengths in order to go through one of these transitions. In order to go through a ground state to an excited state, we need some smaller wavelengths, higher energy light to hit DMSO to get the chromophores to go from one of these ground states up into this excited state. So now that we have a pretty good understanding of how UV detection works, and we went through those chromophores and how those chromophores are going to absorb different wavelengths of light and then are able to jump from a ground state to an excited state, let's start to talk about whether or not you guys should be using UV or UV-Vis detectors. So with a UV detector, you're going to have a range from 200 to 400 nanometers, and with UV-Vis, then we're able to expand that range and go from 200 to 800 nanometers, including that visible spectrum. So in order to look at these and really dive into both of these about which one you guys should be using, we used an example. We looked at experimenting between the two different types of detectors with a couple different dyes. So with this dye, we had some brilliant blue. So if you look at the structure there of brilliant blue, you can see some double bonds, you see some non-bonding pairs. So it's going to have some UV detection, but you can also see that it has this really nice blue color. So it's also going to fall somewhere within that visible spectrum. It's going to be able to absorb some of that visible light there as well. We also added some sunset yellow. So again, structure wise, you see some double bonds, you see some non-bonding pairs, and of course you see that yellow orange color. So it's also going to be able to absorb somewhere again on that visible spectrum. And then our third component, our third dye we added to this mixture is that Allura red. Again, really nice red color. You see lots of double bonds, some non-bonding pairs as well. So each of these three dyes are going to have some sort of UV absorption, some sort of UV response, along with some sort of visible spectrum response, allowing us to look at the UV detector and then that UV-Vis detector as well. And of course, we ran these on our Combi Flash Next Gen 300 Plus. We dissolved these dyes within methanol and then ran these different dyes on our C18 columns. So here are our results from the initial separation of that dye mixture. You can see that with our UV detector, we're looking at our red trace at 214 nanometers. Our purple trace is going to be at 254 nanometers, and then we have an all wavelength detection set at 200 to 400 nanometers. So with this chromatogram, you can see that we get a peak here with our sunset yellow followed by our Allura red, and then we get our brilliant blue peak. And for the UV detector, we cut peaks and we did peak collection based off our 214 nanometer absorbance. So you can see where the Allura yellow, or sorry, excuse me, the sunset yellow comes out, we get that peak collection, and then our Allura red goes about to that 4.5 minute mark, and then that peak is cut off, and then we get our brilliant blue peak collection there. Now if we then transfer and look at our UV-Vis detector, you can see that we've changed our wavelength. So now that red trace is going to be at 500 nanometers, this purple trace is going to be at 620 nanometers, but we're going to keep that all wavelength detection the same, and we're going to keep that at 200 to 400 nanometers, so you guys are able to compare that first separation then to the second separation with UV-Vis. Now we use this 620 nanometers now to determine peak collection. So we only collected peaks for 620 nanometers, and you can see that here, starting a little bit before that 4-minute mark and ending after that 7-minute mark, to try to really collect all of that brilliant blue dye and increase that recovery number for that brilliant blue. But you can see here, and we'll get into this in this next slide, you can see that we have some overlap if we're looking at this UV-Vis detector and just basing our peak collection off of that 620 nanometers. So with this slide here, we looked at those fractions that we collected on the previous slide from our brilliant blue, and then we ran those fractions again on the same C18 column, this time using that UV-Vis detector for both of our different fractions. So the chromatogram on the left is a zoom in portion of our chromatogram where we took that UV collection of our brilliant blue, added that fraction back onto our C18 column to just see what type of separation we were getting from that aurora red, that sunset yellow from our brilliant blue if we're just looking at our UV detection. Again, we use that 214 nanometer to collect and base peaks off of on that UV spectrum. So here's this UV fraction, and you can see we get a nice peak as we would expect with that brilliant blue. And as I highlighted on the previous slide, that UV-Vis fraction, if we load that back onto the C18 column, you can see that we have some carryover from that aurora red. But I will mention with the UV-Vis, since we were able to collect peaks based off of that 620 nanometer mark, we were able to increase our recovery numbers with the UV-Vis, but we get better purity with our UV detector. So that's something to think about when you're trying to determine whether or not you should go with the UV or the UV-Vis. If you're working a lot with dyes, or if you're working with some of the organic compounds that are going to absorb somewhere within the visible spectrum, maybe you do go with the UV-Vis detector. It might cost you a little bit more, but maybe you're able to increase your recovery numbers. But if you're not working really within that visible spectrum and you're not seeing dyes or anything that has a visible color to it, you can get just as good separations with that UV detector, again, because a lot of the compounds we work with, whether it has visible detection or not, it's going to have some of those double bonds or those non-bonding pairs where you're able to get some sort of UV detection, and then you're able to cut peaks and get recovery based off of just its UV instead. Now let's talk about all wavelength detection. If you guys remember from those previous slides just a little bit ago, that yellow trace, that yellow UV trace on both the UV and the UV-Vis chromatograms, that was our all wavelength detection. So what is this all wavelength detection? All wavelength detection is going to be an average of the absorption for the wavelengths that you specify within that range. So this is going to be useful when you're dealing with a compound and you're not sure what the UV spectrum of that compound is. You're facing a little bit of the unknown. This is where all wavelength collection can be handy, and it can increase the signal for low absorbing compounds. So in this example here, we have cholesterol. So the structure for cholesterol is shown down in that bottom left hand corner, and you can see that it has one double bond that we can use for UV absorbance. So when we run cholesterol on our CombiFlash next gen unit, you can see that we get really low UV detection. You can see that absorbance on that y-axis there. We're down to the 0.02, 0.04 is about the highest we can get at 200 nanometers, and 210 nanometers we're not even getting to that 0.02 mark. So what we're able to do with all wavelength detection is then increase that signal, because now we're looking at a range from going from 200 to 210 nanometers, and you're able to see that we're able to then increase that signal, get it up to 0.06 with that all wavelength detection. So if you have a compound that you're not sure what the UV spectrum is, this is a great resource, because you're able then to go from 200 to 400 nanometers along that whole UV spectrum, spectrum and see if you're getting any sort of absorbance within that spectrum. It's a lot easier than just trying to guess and check with multiple different wavelengths. Check at 250, you don't see anything there. Try again at 280. All wavelength detection is able to do that for you. And then again, if you have a compound with just low UV absorbance, you can then create a range of wavelengths that you're looking at, and that average is then going to increase that signal, which is going to lead you guys to better purity and more clean fractions. Now, another area where you guys might want to use all wavelength detection is when you have saturated the UV detector. So all wavelength can offer a lower signal when that UV detector is saturated. Again, because we are taking the average of whatever range you guys put in for all wavelength, and we're averaging those wavelengths. So here you guys can see that we have a separation between catechol and resorcinol, and these two different compounds, they have plenty of double bonds where we can absorb. So in this separation here, if we just looked at that 207 nanometer mark, that gray trace, you can see that we are saturating that detector, and we're not getting good baseline resolution. We're not getting really any resolution at all between those two peaks, so it's going to be very hard to cut peaks and get any sort of good pure fractions out of that. But if we use all wavelength, then we're able then to look at a range going from 200 to 400 nanometers. Well, these two compounds might absorb really well at 207 nanometers, but if you add the wavelengths from 210 on to 400, well, that's going to lower that signal, because again, we're taking the average of all of those different wavelengths. So that's able then to drop that UV signal down to where we're able to get to baseline resolution between these two different compounds. And this was ran on our AccuPrep HP150. So I don't want you guys to think that all of these UV tips and tricks can just be ran on our flash system. All of our UV detectors are used throughout all of our different systems. So if you're looking at next gen, you can run it. You're looking at an AccuPrep 150 or the 125 or even the SFC. All of these wavelength tips and tricks can be used on all of our different systems. Another possible reason why you guys might want to use all wavelength detection is if you guys are looking at compounds that are very similar to each other and are going to elute at similar times. So in this example, we're going to look at caffeine and theophylline, and you guys can look at those structures. They're very similar to each other, so they're going to elute very close to one another. So we created a mixture of caffeine, theophylline, dissolved those in methanol, then added them to a silica column on our AccuPrep SFC, and we wanted to see what all wavelength peak collection would look like compared to collecting with 214 nanometers. So that's what we did here with this chromatogram, is we cut peaks based off of that 214 nanometer wavelength, which is our red trace shown here. And you can see that we go from collecting that caffeine peak straight into collecting that theophylline peak. There's no gap in between if we're just cutting peaks based off that 214 nanometer wavelength. And down below, you can see, similar to our last example, how that all wavelength detection is going to drop our UV signal. So what happens if we use all wavelength detection then to actually cut and collect our peaks? Well, that's what we show here. So in this example, we're using that all wavelength to cut our peaks. So we go from that caffeine peak, and then that caffeine peak is going to stop being collected, and then there's going to be a gap, and then we're going to be able to collect that theophylline peak. So since we have that lower UV absorbance with the all wavelength, we're actually able to get better resolution, better peak cutting with all wavelength here. And again, that can be shown when we zoom in here. You can see that gap and how well that chromatogram on the right, based off of that all wavelength detection to cut those peaks, is doing for that first caffeine peak. You can see it ends exactly where it's supposed to end, where if we look at the chromatogram on the left, you can see that we are collecting some of that theophylline peak within that first fraction. So what we did here is we looked at that first fraction, that caffeine peak, and we wanted to see if we could quantify how much theophylline, how much caffeine was within that first fraction. So we added that to our analytical system in the lab, and we ran those, and you can see here on this chart that 214 nanometer used to cut peaks, it was allowing us to collect more of that peak number one, that more of that caffeine, but it's only a difference of 4.2%. So if you use 214 nanometers to collect your peaks within that example, you're going to get 4.2% more caffeine within that first fraction. The big difference, and we kind of hit on this earlier with those chromatograms, is the amount of theophylline in that first peak when you're looking at that 214 nanometers to cut those peaks. So if you're using 214 nanometers to cut those peaks, since you saw that increase in UV signal, you're going to actually collect 80.1% more of that theophylline within your first fraction if you are using all wavelength to collect those peaks. So if you're using similar compounds or trying to separate similar compounds, all wavelength detection can be a tool for you to try to increase the purity of your fractions. Next, we're going to look at baseline correction and how baseline correction can help you guys if you guys are using solvents with some sort of UV absorbance. So as I mentioned, baseline correction is going to be useful when you guys have a solvent that has some sort of interference with your compound's maximum absorbance. So if we look at a couple different compounds here, we'll look at phenacetin that has a maximum UV absorbance at about that 250 nanometer mark. And then we look at N-benzyl benzamide, which has a strong maximum absorbance at that 214 nanometer mark. And we run those in normal phase, and we're using ethyl acetate as our strong solvent. Well, as I mentioned previously in this webinar, ethyl acetate is going to have some sort of UV absorbance below that 240 nanometer mark. So if we're looking at N-benzyl benzamide, it's going to be really hard to distinguish between what's ethyl acetate and N-benzyl benzamide just because they're absorbing at that same wavelength. Phenacetin has the advantage because it can look at that 250 nanometer mark, and ethyl acetate is not going to interfere at that 250 nanometer. So if we run these compounds on a silica column on normal phase type solvents, hexane, ethyl acetate, on our CombiFlash next gen units without baseline correction, this is something that you guys might see. You can see that 214 nanometer, that red trace there, is going to slowly increase as we increase that percent B in our solvent composition. And that's our ethyl acetate. That's that UV absorbance due to that ethyl acetate, that rising baseline. And you can see, especially when we get to that second peak there, if we're just looking at 214 nanometers, we're not able to cut that peak. We might be able to cut that first peak there, but that second peak, we're not able to cut it just because of that interference from that ethyl acetate. But if we run baseline correction with this, what baseline correction does is it looks at how these different vectors based off of this UV signal move within space. So we're able to distinguish between what actually is a solvent and what is actually a compound being eluted. So if we run baseline correction with these two different compounds, this is something that you guys will see, and you can tell here that we're actually able to distinguish both of these peaks. So you can see we get our nice N-benzyl benzamide compound coming off first, and then that phenacetin's able to cut off as well later. So this is something that you guys will see. And yes, the peak shape is going to look a little bit different than what you guys are typically used to seeing. But if you have a compound that has a maximum absorbance, as I said, along with that interference from the solvent, that's something you guys might want to look at. And if you guys do run into that situation and you guys have to run a wavelength where your solvent's absorbing and that's the only way you're able to see your compound absorb, and you guys run baseline correction and you guys flatline, something I would recommend is try to increase that amount of sample that you're adding onto your column, because then that's going to increase those vectors for that compound, and then your next gen, your SFC, your HPLC 150 is going to be able to better distinguish between what's solvent and what's actual compound. So if you guys are using baseline correction and you're not seeing any sort of peaks because the baseline correction is subtracting all of those different vectors, try to increase the amount that you're loading onto your compound, because that's going to allow peak track and our different systems to better distinguish between what's actually compound and what's actually solvent. Now let's review what we learned about UV today and how understanding UV can lead us to sharper peaks in all forms of our chromatography. We first talked about what UV is and how UV detection actually works, how we're actually measuring the transmittance rather than the absorbance. We also looked at how different wavelengths can be used for different compounds and how these different chromophores can be absorbed and go from a ground state to an excited state, and which ones you guys should be looking at in terms of UV absorbance. We looked at that 3 different dye mixture and showed you guys the difference between UV-Vis and UV, and how UV-Vis actually had better recovery of that brilliant blue, but it didn't have as good a purity as that UV detector. So that's something to keep in mind if you guys are looking at UV-Vis versus UV. If you guys are using compounds that have some absorbance within that visible spectrum, UV-Vis will definitely open up some doors that you wouldn't have with UV, but UV can still detect the same compounds that UV-Vis would. We also talked about whole wavelength detection and those different examples. We looked at cholesterol and how using a different range going from 200 to 210 nanometers can actually increase your UV signal seen for cholesterol and other low absorbing compounds. We looked at that catechol and resorcinol example where all wavelength did the exact opposite. Instead of increasing that signal, we actually were able to decrease that signal to get better resolution between those 2 peaks and get better purity within our fractions. And the same could be said for that caffeine and theophylline example as well. If we used all wavelength detection to then cut our peaks instead of that 214 nanometer wavelength to cut our peaks, we saw less theophylline within our caffeine peak and we saw better purity. We then looked at baseline correction, and we talked about how these different vectors move within space, and then within these vectors we're able to determine what's actually solvent and what's actually some of your compounds. So we looked at that phenacetin and that N-benzylbenzamide example to show you guys how baseline correction can be done. And if you guys are working with a compound that absorbs within that solvent system, baseline correction might be a handy tool for all of you guys. As I mentioned in the beginning of this webinar as well, we are now Teledyne Labs. So with new rebranding comes a bunch of new social media handles for you guys to follow. So make sure you guys get on Facebook, X, LinkedIn, YouTube. We are now Teledyne Labs and not Teledyne ISCO for chromatography. So be sure to follow Teledyne Labs on all of the media. This is where we're going to post all of our updates, all of our webinars, and all of our news. So be sure to give these new handles a follow as well. I'd like to open the floor up to any questions you guys may have. So now's a perfect time to type your questions into that question tab, and we'll get to answering a few of the questions that you guys might have. And if I don't get to some of the questions by the end of this Q&A section, I will answer those by email the next couple of days. So now's a perfect time to type in those questions into that questions tab, and we'll get going here. First question I see popping up is, what if your guys' compounds don't have any chromophores and you guys don't have any UV absorbance due to your compound not having those chromophores, not being able to go from that ground state to that excited state? And we have a couple different options here at Teledyne Labs. The first thing you guys could look at is working with an ELSD. So a lot of our systems can come equipped with ELSDs. Now, the only thing to keep in mind with an ELSD is you have to work with some non-volatile compounds. So if that's what you're working with, that's a great option. You could also look at using mass spec, which we can also use with a lot of our systems here at Teledyne Labs. Now, the other thing to keep in mind when you're working with these different types of detection methods is that the nice thing with UV detection is it's non-destructive. So you're just sending your compound through that flow cell so it can get detected. But with a lot of these other detection methods such as the ELSD, the mass spec, you're going to lose a small amount of your sample because these are destructive techniques. They're going to destroy your sample in the process of being detected. So that's something to keep in mind as well. But if, yes, you don't have any chromophores within your compound and you're not getting any sort of UV signal, we're going to have to look at other detection opportunities and instruments, and that's the ELSD and that's the mass spec. Another one coming in here is if you have low UV signal and you're struggling with cutting those peaks, is there any way to improve low UV detection and peak cutting? And one thing I could think of and tell you is you guys can adjust your threshold, whether you're cutting with a certain wavelength or if you're looking at all wavelength detection, you can lower that threshold in order to cut your peaks. So you can drop that threshold and then you're going to start peak cutting or peak collecting earlier than you would. So if you increase that threshold, your peaks are going to cut a little bit later as it passes that UV threshold. But if you drop that, you're able to then collect peaks sooner and then also extend your peak collection because that threshold's lower in that UV absorbance. Another question coming in here is if we don't know the wavelengths of our compounds, what wavelength should we use? And if you guys know that you guys have a chromophore within your compound, you guys can use all wavelength detection. As I mentioned, do a scan from, if you're using UVs, 200 to 400 nanometers, and see if you guys can see any sort of peak within that all wavelength detection. Another thing to mention is the most common wavelength that a lot of people are going to use is 254 nanometers. That's probably the most common within UV detection, and that just gets you away from some of the higher energy wavelengths that can also absorb a bunch of different compounds. It's a good intermediate at 254. The other thing you guys can do with all of our Teledyne Labs systems is you guys can look at the UV absorbance at a certain point within that chromatogram. So if you do get an all wavelength peak somewhere within your chromatogram, you don't always have to run all wavelength detection going from 200 to 400 nanometers. What you can do is then you can go back to that all wavelength peak, click and drag, and then look at the UV spectrum there, and then you're able to see that complete spectrum for that compound. So you could have a really nice peak at 230 nanometers, and that's your maximum UV absorbance. So then going forward from there, you can just set your UV wavelengths at 230, and then you don't have to use that all wavelength detection anymore. So that's it I'm seeing for questions. So if you guys do have any more questions, feel free to type those out and I'll be sure to respond to those by email. You guys can also reach out to me directly. My email is up on the slide there, so I will try my best to respond to those questions in a reasonable time frame to make sure that all your guys' questions are answered. Thank you guys so much for joining us. I hope you guys enjoyed this first webinar for 2024 with Teledyne Labs and this chromatography section. So I appreciate it, you guys. Hope to see you guys again next time.